thank you for coming. I appreciate these are very long slots, so it's quite a time commitment at a conference like this to actually come to one of these slots, so thank you very much for turning up. Serverless APIs in Swift. Let's go through the three key words there. Let's start at the end. Anyone here written any Swift before, the Swift programming language? Anyone written some? Just a couple, okay. APIs, anyone here write web-based APIs, HTTP APIs? Again, just a few. And serverless. Was everyone at the keynote yesterday morning? Right, so you all know what Amazon's serverless looks like. So, cool. So this is going to be a talk about serverless APIs in Swift. So at the demo thing, keynote thing yesterday, they showed you event-based serverless programming. That's a very interesting area of serverless programming. I'm way more interested in APIs. That's where I make my living. So I'm far more interested in using the serverless platforms looking like normal web-based APIs. So that's what we're going to discuss today, and we're going to discuss it in Swift. Is that the button? That's the button. Okay, so let's start with Swift. What's Swift? From Swift.org, Swift is a general-purpose programming language built using a modern approach to safety, performance, and software design patterns. That's a really generic phrase, isn't it? It works really well on a website. It doesn't tell you anything. What do we mean by that? The important things there are that it is modern and it is type-safe. So it's a modern native language. There are three good modern native languages that we talk about in this space. Those are Rust. Has everyone heard of Rust from the Mozilla people? Go. You've probably heard of Go because they're backed by a remarkably large advertising company. And there is also Swift, which is backed by Apple. I happen to like Swift the best. It fits the way I think. But the three languages are remarkably similar in their characteristics. Swift is open source. It was created by Apple. It is Apache 2 licensed. That means that all the source code is on GitHub, can't be taken away from us. It has an open design evolution system. So in order to have a new feature added to the Swift language, a GitHub repository called Swift Evolution is used, where the proposed new feature is created as a markdown document, specification of the plan for the new feature, and then the community can comment on this proposal, improve it, and then the core team, the Swift core team, will decide whether to accept the proposal into Swift language or not. When I say it's an open design, I mean even all the Apple employees have to go through this process. So if Apple want to add a new feature to the Swift language, they also have to create this open proposal, have the community comment on it before it adds to the language. So that's quite a nice system. I'm very much into the open source world. I like open source languages, open source frameworks. I don't think I'd be interested in Swift if it wasn't open source. It's also cross-platform. It runs on Apple's operating systems, obviously. I've never, ever coded it there. So I'm willing to bet that those few people who put their hands up saying that they do Swift have all coded on an iPhone. Am I correct? Yes. I've never done that. The only Swift programming I have ever done has been on Linux. So Swift is natively compiled to Linux. It works well on Linux. It's quite a nice language on Linux. You don't have to have a Mac to use Swift at all. It's just not a requirement. There are ports, Android, ARM for Raspberry Pis and other little embedded things, FreeBSD, there's a Windows port on the way. So it is becoming more widely compilable. So it's quite an exciting language. It's also really new. It's only been open source since the end of 2015. So we're about 18 months into this language as an open source Linux language. Benchmarks. With a benchmark, I can prove anything I like. So do not trust anything that I might say at this point in time, because obviously I have cooked the numbers. There's a really useful website out there, benchmarksgame.alioth.debian.org, which has got an awful lot of benchmarks for an awful lot of languages for an awful lot of algorithms. So you can go to that URL at the bottom there and look at the numbers from which these graphs came from. These numbers were taken about 6 months ago or so, so they might be slightly out of date now. And you can look at a load of different algorithms and see how different programming languages compare against each other for different algorithms and how they stack up. In this particular case, we've picked the spectral norm algorithm, which is relatively CPU intensive, quite a CPU intensive algorithm. And then we've picked an arbitrary 3 languages to compare against Swift. So over on the right, we have Ruby to represent the scripting languages. So Ruby, Python, Perl, PHP, they're all in the same sort of ballpark. So the performance, the time it takes to run this algorithm, 134-ish seconds. It takes a while. The scripting languages are not necessarily the fastest languages in the world when it comes to CPU-intensive tasks. Everyone's heard of Node.js? Let's face it, JavaScript is a very key language in the world now. So JavaScript is remarkably more efficient than the other scripting languages. Probably because it runs in the browser. It's the only language that runs in the browser. So that means millions of dollars have been spent making it fast by Apple, Google, Mozilla, Microsoft. There's been a lot of research into making JavaScript fast because it runs on the browser. I hope you can still hear me. So that's why JavaScript is down in the 15-second-ish mark for this particular CPU-intensive algorithm. Then we get Java and Scala and all the other languages on the JVM. And we've also got Swift down here as well. We've got Go, we've got Rust. They are all around the same sort of number, 4-ish. So Swift is a fast language. It is natively compiled, it is quick. So that is important. Incidentally, if you're writing C or C, any C++ programmers? You're down here, you can barely see the number. It is so fast in C. This is what the memory usage looks like for the same algorithm. Again, the scripting languages use more memory because they're duck typing. They are type flexible. Let's put it like that. You can do lots of interesting things with the scripting languages, but they are not particularly memory efficient. JavaScript is okay, not bad. Again, all those millions of investment dollars have turned a relatively efficient memory usage model. Java, however, is less memory efficient than JavaScript for this particular algorithm because, don't remember, benchmarks can prove anything that I wouldn't. As a general rule of thumb, in order to get the speed out of Java, we use more memory. It's a simple trade-off. In the JVM, put more memory at something, we'll get a faster output. And then we get the compiled languages, the Swifts, the Rust, the Go's, etc., much less memory. So we have in Swift a memory-efficient language and a fast language. Now, if you were at the keynote yesterday, you may remember something about serverless, which was how you pay for it. Do you remember how you pay for serverless compute time? You pay for it on duration of time that your program runs within a memory constraint. So you can buy 128 meg slots, 256 meg slots, 512 slots, 1 gigabyte slots, 1.5 gigabyte slots of memory, and then however many 100 millisecond blocks of time your program takes to run, that's how much money you're going to pay for that execution of that particular application. So in the serverless world, a low memory, fast language is cheaper. Which is why Go is also very interesting as a serverless language. JavaScript is pretty good, it's not too bad. That's why you see a lot of JavaScript out there, but mostly because of mindshare. I would not recommend doing Python in serverless or Ruby. They are not particularly good languages for the cost model of serverless. If you don't care about the money, then it's fine. They are far easier to write your application in, but they are not very good from a cost performance point of view. So be aware of that. Okay, so back to Swift. These are the major features of Swift. We have strong typing. It is a statically typed language. It is strongly typed. Once you have defined a variable as an integer, you cannot assign a string to it. So, one of those sort of languages. Has type inference. That means that we don't have to waste our time writing that that variable is an integer if we assign 42 to it. If we assign 42 to a variable, then clearly it's an integer. So the language knows and can work out the type intuitively, it can infer it. Optionals are the idea that we cannot have a variable that is null. In Swift they call it nil, but it's basically the same thing. If a variable is null, the compiler wants to know that that is possible, and you can, if a variable is not an optional, it may not be null. This wipes out a whole class of bugs, which is quite nice. Other languages have this as well. Rust has it, I believe. Scala has it. There are in a few languages. It's quite a nice feature of a modern programming language. Everyone knows what closure is because JavaScript has them, hence everyone knows what they are. So Swift has them too. They look remarkably similar to every other language in the world. Custom operators. Who was in Damien's talk yesterday? The closing keynote? Is anyone there? So, Damien showed us a C++ application where he had taken operator overloading to an extreme level. Try not to do that in the real world. But the nice thing about custom operators is that you can define or redefine things like the plus sign for your own object types. So, for instance, we could create an object type called money, and then we can implement a plus sign operator so we can add money together. So we can create quite an expressive language with custom operators and operator overloading. Just be careful because it can be abused. The C++ people in particular seem very good at doing extreme stuff with operator overloading. Tuples, another fairly modern thing. Python has them as well. Rust does, etc. It's the idea that we can have more than one variable that must always exist together. So we have multiple variables and they are grouped. You can't have one without the other. Generics are a strict typing language feature for custom algorithms. So if I've got some sort of algorithm that does something, and I want it to work for integers, and I want to work for floats, for instance, and I want to work it for doubles, I don't want to have to write it 3 times, just because the type has changed. So generics allow me to write the same algorithm once, the same bit of code once, and tell the compiler that this algorithm will work with multiple different types of variables. Finally, Swift is very interoperable with C. Most of the core libraries that you get in the average operating system have got a C interface. So having a good interoperability to read C code and use the C library in your application is very, very helpful. And Swift is really, really good at that. Swift also interoperates with something called Objective-C. Realistically, nobody cares. Well, you iOS people probably care quite a lot. Those of us on the Linux side couldn't care less. Keep pressing the wrong button. So back in that original definition, there was the word safety involved. And the word safety has got different meanings for different people. So I'll just quickly go over what I mean by safety and what the Swift people mean by safety, maybe, in terms of the language. And firstly, we talk about type safety. We're not going to try and add a string to an integer and get confused, or we're not going to do a JavaScript. You've seen the JavaScript thing with adding numbers and strings. Weird things happen. Can't do that in a type-safe language. Swift has a philosophy of preferring constants over variables. So there's a keyword called let, and there's a keyword called var for defining a variable. And you'll see a preference in the Swift programming community for let over var. A tendency to prefer constants and immutability wherever possible. And again, that's one of those things which, once you've got your head around it, reduces the chance of bugs, reduces classes of bugs that you're going to have in your application, because if you can trust that a given variable can't change, it's constant, then it's easier to reason about. There's less testing required because it will always be the same thing. So that can be quite helpful. Variables have to be initialized before use, which comes back to the whole optionals thing. You can't declare a variable without saying what it is unless it is an optional, i.e. it may be null. And again, that awareness of whether something is null or nil makes it much easier to ensure that you have covered the scenarios where you're trying to dereference a null pointer or trying to call a method on a null object or something like that. Those sort of things that blow up in the scripting languages. That's what I mean by safety. It makes it a little bit easier not to screw up. Trust me, you can still screw up. Any programming language, it's trivial to screw up. So let's look at some Swift code. Traditionally, I would put hello world here. But realistically, in every programming language except for maybe C++, hello world is the most boring application in the world. It is tedious because it's a single line, print hello world. Pretty much every language. So let's do rock, paper, scissors. So we all know what rock, paper, scissors is. Very simple game. A little bit of code, it's not very long, only 12 lines here. Import foundation. Import is a keyword that allows us to bring in other packages or libraries into the scope of our application. So I'm importing the foundation library, which gives me access to the standard library type things. There's one let keyword on line 3. Let shapes equals rock, paper, scissors. I've defined an array of 3 elements. Because it is a let rather than a var, I cannot change it. I can't modify it. I can't make it bigger. It is always going to be an array of 3 elements. For loops. We've all got a for loop in our languages. So lines 5 through 8 simply do a for loop. We're counting to 3, 1 dot dot 3. And the 3 dots means it's inclusive. So it will count 1, it will count 2, it will count 3, and assign it to the count variable. If I wanted it to be not exclusive, it would be dot dot less than, and then it would count 1, then it would count 2 only. You can guess what the print keyword does. It's a function call, calls print. And then the sleep keyword, our sleep function, you can guess what the sleep function does. Sleeps for a second. Lines 10 through 12 are our actual application. All that stuff is set up and boring stuff. Line 10, we seed the random number generator. You can see we've imported foundation, so we have got an object called nsDate, which is a date and time class. I grab in the number of seconds since 1970. Type safety. srandom takes a uint32, so I have to cast the integer that comes out of time interval since 1970 to the right type so that Swift knows what's going on. I've seeded my random number generator. Line 11 picks a number between 0 and 3. That's what the modulo does. And then we print out the particular choice. So nice little application, doesn't do very much. This is how we run it on the command line. Keyword is Swift, that's the name of the compiler. Pass in the Swift file, and it will execute it directly. So Swift, rock, paper, scissors, dot Swift, and it'll immediately execute 1, 2, 3, scissors, in this particular case. We have that. Right. So there's the fundamentals of Swift. Let's talk about a few other little bits of interesting things. Structs are Swift's value objects. If you look at that code, pretty much every language that's a braces language looks probably fairly similar. You know, we can see on line 3 we're defining a property. Line 9 to 11 we've got a method within our structure. Lines 5 to 7, init is a constructor. So a struct within Swift is very, very similar to a class in every other language. If you're a C or C++ programmer, you'll know that a struct is something slightly different. You don't have functions within structs in C. You do within Swift. It looks like a class. In fact, it pretty much can do everything that a class can do. The only key thing about it is that it is a value object. Have you come across value objects? Anyone know what a value object is? Value object is an immutable object. And in Swift's case, that means it is passed by value. And we'll come on to that again in a minute. Just remember that structs look like classes, and they are essentially immutable. Here's how you would use one. Let £5 equals money, amount colon 5, currency.gbp. So I'm English, I don't know if you could tell from my accent, but I come from England, and great GBP, British pounds, £5. It used to be a lot of money, it's not worth so much nowadays. What can you do? Again, we've defined a constant, an immutable variable, by the let keyword. There's no new keyword. We don't have to instantiate with a new keyword. It's modern native language. Swift knows that you're obviously instantiating an instance of the money class because that's what it looks like. I'm assigning a money to a variable or to a constant. Therefore, I must be instantiating an instance of this object. Hence, we don't need to say so. Notice that we have to label our parameters when we call a function. So here I'm calling the money's constructor, the initializer, and I have to pass in the amount colon and the currency colon as labels to the parameters. Swift is a very expressive language. It tries to make it clear what is going on, and that is one of the features of the language. If you were in Damien's talk yesterday, he talked about being able to swap parameters around. You can't do that in Swift. If amount is defined first and currency is defined second, they have to be in that order. And then just print it out, compile and run it. Yay, we get 5. Swift does have a class keyword. So classes are objects that are reference objects. So once you've instantiated an object and pass it into a method, the same object comes with you. It's not done on copy. And the other key thing about a class is that you can inherit from them. So if you want a parent class and a child class, you have to use the class keyword. You cannot use the struct keyword. That's about it. Fundamentally, they're basically the same. So here I've defined a child class. We've got a name and we've got an age, a couple of properties, and we've got an initializer so we can set them. So nothing particularly complicated. Usage looks a bit like this. So here I've got a child called Judith who is 12, and then I assign Karen to Judith and change Karen's name to Karen, who's now also 12. If I print Judith's name and I print Karen's name out, you will notice that both objects have the name Karen. That's what a reference type does. Although I've assigned Judith to Karen, Karen is just a reference to the same object as Judith is a reference to, the same instance. Hence, the name is shared between them. That's what reference types look like. Value types, however, are copied when you do the assignment. So if we go back to our money structure and have my £5, I assign my £5 to a £10 variable, change the amount to £10, and now when I print out the amount, I get £5 and £10. I don't change the £5 instance of the money structure because it is a value type. These are very powerful features. They're in pretty much all languages, so maybe some are scripted ones. But being aware of what you've got and which one you're using can be extremely helpful. I quite like these features. Last thing I want to mention about Swift programming language, I appreciate that this is not even an overview. This is a tiny snippet, a little bit about what I find interesting about Swift. Something called protocols. Every other language calls them interfaces, but they're called protocols in Swift. Just be aware of that. It is basically an interface. An interface has methods, it has properties that suit a given task, and then we implement that interface within our class or our structure. In Swift, we call that adopted. We adopt a protocol. In every other language, like Java or something like that, we implement an interface. Same basic concept, different words. So here I've got a protocol called JSONable. Whatever you do, never label a protocol like that. It's a horrible word. And all this protocol does, line 2, is define a function called toJSON, which must return a string. So you can imagine what this protocol is for. It's to enable me to have a JSON representation of any given object that adopts this protocol. As an API person, being able to get JSON representations of things turns out to be quite helpful. To implement the protocol, or to adopt the protocol, we use a colon followed by the protocol name. So you can see here, colon JSONable. We have adopted the protocol. Because we have adopted the protocol, we have to implement the function. Otherwise, the compiler gets upset. That's all fine. That's nice. That's very predictable. We're all quite happy with that. Really nice thing about Swift is that keyword there, extension. I can adopt a protocol for a given class definition or struct definition in a different code file. So I can extend the money structure to make it JSONable in a different file. You say, well, so what? Well, the really nice thing about that is that I can do that for any class in Swift. So Swift has got a class called dictionary. It's built into the language. As a Swift developer, I can extend the built-in dictionary class and adopt my own protocols without changing any of the code provided as part of the standard library. That's a really powerful feature and quite helpful. The classes are a little bit open like that. Now, I haven't mentioned access control. Access control in Swift there's quite a lot of it. So you need to have the right sort of access control keywords on your classes to be able to do this. So I can define a class that you can't extend if I wanted to. But as a general rule, within the language, we have this sort of feature, and I like it a lot. So as I said, I've not really talked much about the language itself. So if you want to learn Swift, these aren't a bad set of references to look at. Apple provides the first two. Right. The Swift programming language, Swift 3 edition now, is an ebook, it's a PDF, it's a set of HTML pages on somewhere on Apple's website. It's really well written. If you want to learn the Swift language, that book is worth reading. It's easy to read, it's very clear, it explains how the language works. Worth your effort. App development with Swift is more of a teaching book. It's designed as part of the Apple iTunes University sort of environment. It's very good if you're as a teaching type of book. So if you learn more as you get taught, then that's not a bad book to read. If you like third-party people's books, then O'Reilly have got Learning Swift 3. I'm pretty sure they've got some over at the O'Reilly desk today. That's not a bad book. Jonathan Manning, Paris, and Tim are very good Swift programmers. They know what they're doing, and they're fairly well written. It's fairly easy to read, easy to understand what they've written. And finally, a self-published book, Wayne Bishop's Swift Algorithms and Data Structures. If you want to deep dive into Swift algorithms and doing sort of complicated stuff in Swift, that's not a bad book to read. Okay, let's talk about serverless. I hate this word. So, serverless. The first thing to know about serverless computing is that serverless is a pretty bad name to call it. Obviously, there are servers involved. We're stuck with the word. We have to live with it. You notice that a word gets adopted for something and you can't change it ever again. We get this word and we're stuck with it. So the word is serverless. It's not a particularly useful word to use. It is the one we're stuck with. Slightly better phrase is functions as a service, and that's still not very good, but at least we're in the right ballpark. Essentially, a serverless platform is one where you have to write just the code you care about. It's a runtime. You write a function, or a group of functions, but essentially a single function is called, which takes some data and you give some data back, and the rest of the system worries about everything else. You don't have to worry about provisioning, you have to worry about virtual machines, you have to worry about containers, you don't have to worry about routing. Magic happens, and by magic I mean someone else's problem. I'm a big fan of this idea because I am not an ops person. DevOps is a thing. I don't care. I would vastly prefer to never ever have to think about a container in my life. I don't think that's my problem. My problem is solving a business use case. My problem is creating a solution for a given algorithm or given problem. It's not particularly about worrying about capacity. That's not really my problem as a developer. So if I can abstract that away, commoditize it, and make it someone else's problem, I am all over this idea. Just your task being executed. And the other thing I really like about serverless is the payment model. You only pay when your code is being run. So I'm not paying for a machine to sit there doing nothing, waiting for an API call to hit my machine. Not my problem. I only want to pay when my code is doing something. Why should I pay when it's doing nothing? Let that be someone else's problem to deal with. So I quite like it as an idea. 3 obvious use cases. These were covered in that keynote yesterday if you were there. Synchronous. This is the same basic idea of a normal API. Service is invoked, it provides a response. Very, very standard, normal thing. HTTP requests are the obvious ones. Displaying a web page, a standard web API. They all work the same way. You send a request in, you get a response back. Synchronous, happens immediately. Asynchronous, some sort of message happens, which drives an action, and then some point later, things happen more. This is a whole event-based system. This is the one that we always use in the demos because it looks cool. A GitHub, you push something to GitHub, a webhook comes out of GitHub, it hits your serverless functions, they do some stuff, and the notification ends up on Slack. That's an event-based system. Quite cool. I don't do a lot of that. Most of my stuff is synchronous, that's what we're going to be talking about. But serverless is really, really good at that as well. Because again, you're spending a lot of time doing nothing, and you're not paying for it. Lastly, the concept of streaming, continuous data flows of stuff to be processed. So you've got queues of things in messages or in Kafka or in whatever Amazon's thing's called. And they need to be processed and put somewhere else. Serverless is quite good at that because it scales really, really well. We can very, very easily run 10,000 instances of our code, and we don't have to do the work. It's not our problem. The serverless people magically scale our function up. I keep using the word magic because I'm not a DevOps person, as you can tell. I'm not an ops person. This is someone else's problem. I love it not being my problem. So there's the common tasks. We just talked about these. Microservices, API backends. You've got to say microservices nowadays, otherwise nobody listens to you anymore. Have you noticed that? Volatile workloads, anything that you can break down into pieces, like data processing, event processing, work really, really well in a serverless environment. Anything that looks like a cron job, they also work well in serverless environments. Again, because you're not paying when it's doing nothing. And everyone loves chatbots because they make great demos. So, ooh, what happened there? This is what happens when you're not using your normal thing. Does that work better? There we go. There are obviously problems. So I've just sold you and told you how great serverless is. Obviously, it doesn't fit everyone's scenario. Serverless is not going to take over the world, and there'll be no other type of computing happening. That's just not going to happen. The obvious problems are there is a startup latency. If your function is invoked when it is needed, it is not there in memory when that initial call comes in. There is a startup latency. If you are writing financial transaction things, your Bloomberg or something like that, that might be unacceptable. So be aware of that. There is a slight delay there. There are time limits. I cannot have a function that runs for more than a few minutes, 5 minutes, something like that. If you can't break your algorithm down into lots of small chunks, you can't put it in a serverless environment. You'd be better off doing it another way. Spin up a VM and do it there. State is external. This may or may not be an issue for you. But after 5 minutes, you lose everything. So once your function has finished running, it is thrown away, essentially. If it is thrown away, anything you've got in memory is thrown away too. There is no state in your functions, in your application. If you need state, you have to store it elsewhere. You have to store it into Memcache or into Redis or into somewhere else, a database of some form. So you have to be aware of that. It's a slightly different paradigm if you're not used to it. A lot of web HTTP stuff is already built around the idea that state is external. So that's one of the reasons why it works quite well for HTTP APIs, because we already think like that. But if your type of application needs internal state, then serverless is going to be slightly more challenging and will require some more thinking about how to do it. So be aware of that. Lastly, although I said there's no DevOps involved, I lied. You still have to worry about monitoring. You still have to worry about logging. You still have to deal with aggregation of logs and tracing things and working out how to debug it. And things are happening on live that don't happen in staging. All those things still happen. Just because it's serverless doesn't mean that the normal computing things magically no longer exist. They do still exist. And because you have broken up your algorithms into lots of little bits, there is a lot more bits to monitor. It's the same as doing microservices in that sense. Monoliths are much easier to reason about than microservices or serverless applications. So just be aware of that challenge as well. Now that famous quote that if you can't build a good monolith, there's no way you'll write a good microservice application. The same thing holds the same for serverless applications as well. So be aware of that. For me, it is all about the value. I do low volume business to business stuff, so it's all about the value. So here's a series of tweets from a guy called Bo. Serverless is a point on the path to true app isolation. Apps just want to run. Their authors don't care about infrastructure. And that to me is the key thing. The app author should not need to know, any more than a journalist knows about printing presses, what the voltage or the power is used, what type of computers we're using. Shouldn't have to care. We're relearning what was known in the timeshare days. Pricing has to be based on something customers value, not infrastructure, not VMs. I value when my code runs. Serverless fits the value model that I care about, that my customers care about. I find it interesting that we are relearning this also. We do this a lot in our industry. We relearn and rename things that we learnt before. Fortunately, as an industry, we learn. We get it better. Each time that we reinvent our wheel, we get better wheels. And I think serverless is quite a nice new wheel. Loads of implementations, alphabetical because I couldn't think of a better way to write them. Apache OpenWhisk is an open source implementation of a serverless compute platform and has two commercial sponsors, IBM and Adobe. So IBM Bluemix OpenWhisk, I think they call it, and Adobe I/O Runtime. Both are the implementations of the same underlying serverless compute platform. AWS Lambda is clearly the market leader. We've all heard of it. I think it's quite good. Google Cloud Functions, Microsoft Azure Cloud Functions. There's clearly some naming going on there, can't you tell? They do the same basic thing. Iron.io, Webtask.io are some smaller players. Iron.io was one of the very early ones. They're all serverless implementations. With the exception of the OpenWhisk one, you've got a little bit of vendor lock-in if you're not careful, so be aware of that. I'm going to talk mostly about OpenWhisk here for two reasons. Firstly, it's open source, and I like open source. The reason I like open source is I can read the source code to work out what's going on. I'm never ever going to write any code contributions into OpenWhisk, but being able to read what it does is quite informative. It has two commercial implementations. That appeals to me because I like the lack of vendor lock-in. If I don't like IBM, I can use Adobe. If I have issues with Adobe, I can use IBM. I quite like having multiple vendors for where I can place my source code. Of course, the main reason I like OpenWhisk is that it supports Swift natively. And if I want to write Swift, OpenWhisk just supports it out of the box. There's nothing complicated to do. But serverless as a platform, pretty much any language you like. Use the language that you prefer. Obviously, we're going to talk Swift today. Okay, let's do some code. If I can find my mouse. There we go. If I click that button there. There we go. Okay, so let's write Hello World as a serverless API implementation in Swift. So vim hello.swift. Can we all read that text? Okay at the back? Bit bigger? Bit bigger. Not that one. Better? Okay. You're going to see quite a lot of console work here, so I hope that's okay. We're all about the Vim today, because I don't have to change Windows too much. Ooh, not that one, that one. Func. The entry point to a Swift serverless application is a function called main. If you're used to C, that should be a very familiar concept. We have the main function, that's our entry point. It takes a dictionary of arguments. So args is a dictionary of string to any object. So what I'm saying there is I've got a parameter called args. It is going to be a hash or an associative array. The key of the associative array will always be a string, but the value for each element in the associative array could be anything. So I define that with the type of any, which means you're going to have to convert it before we can use it. So that's my function, not that one. So that's my function definition. Dash greater than means this is what I'm going to return, and I'm going to return another dictionary of string any. So my function takes in parameters as an associative array and must return an associative array. Nice and simple. Let's define, it's a braces language, so we need some braces. Let name equal args of name. Question mark world. Print hello bracket name. Return a dictionary message hello name. Okay, there we have a complete Swift function, Swift serverless function. We define a constant called name, let name, and then we assign it args of name here. A dictionary is an optional construct, i.e. the arg key may or may not exist within our associative array. It is by definition optional. So I now need to convert it to a non-optional or a concrete string. And the way I do that is using this shortcut terminology, question mark, the null coalescing operator. And what that does is say, if it turns out that args of name is nil, please use the word world instead. So I can guarantee at the compiler level that name will always be a string and that it will be world if name doesn't exist. So that's all that line does. You'll see that sort of construct quite a lot. Print writes to the standard log, to the standard out. So it's just a way to put some console debugging out. And as it's a serverless function, I have to return a dictionary, and I'm going to return a message with hello name on it. Okay? That's all we're doing there. Save and exit. Now, how are we going to run this? We're going to use OpenWhisk. OpenWhisk has a command line tool called WSK because spelling the word whisk was too complicated for the developers. I have no idea why. But we use WSK. If I do -H for help, I get some output. If I scroll down, look, it's even got ASCII art in it. How cool is that? The help for the WSK or the whisk command is really, really good. WSK -H gives you clues of what to do, and I like this feature a lot. So here you can see my available commands: action, activation, package, etc. If I was to type WSK action -H, I will now get the help for how to work with actions. And I can see I've got the ability to create an action, update an action, invoke an action, things like that. WSK action create -H, and it'll tell me all the possible parameters I can use for creating an action. So the help built into the WSK tool is extremely good, which is quite helpful because I don't know what I'm doing. Having it built in is normally quite good for our documentation. Right, so now we need to actually upload our action we've just written and put it into the serverless environment. I've already told you that serverless runs on the cloud, and OpenWhisk is an open source environment, hence I'm running it on this computer. One of the really nice things about that is that if all the internet dies, I can carry on with my demo. It means I can develop locally. I can have a team of developers developing locally their serverless applications, and then we can push it up to the cloud for integration and testing. Have a very quite nice workflow because it is an open source model. WSK, action, update, hello, hello.swift. So update, create, they work the same way. Hello is the name of my action. Hello.swift is the function I care about. So now I've uploaded my Swift code to the cloud, which is run on my machine. How do I run it? How do I test it? WSK, action, invoke. Invoke means to run. Just a complicated word for run, because run was not enough letters in this case. What do I want to run? Hello. Serverless environments are asynchronous by nature. It assumes you want to run it asynchronously. So we have to add a switch, --, blocking, to tell it to run it and wait for it to finish. And then we use --, result to tell it we would like the result to be returned to us. So now we're going to compile that Swift code, execute it on the cloud, and get an answer. Message, hello world. We've just written our first serverless function. They're not particularly complicated. Now if I go to this tab here, WSK activation poll is like doing a tail -f on your logs. Has everyone heard the word, have used the command line tool called tail before? Tail -f, put it against a file, and anytime new stuff is written to the file, it will display on the screen for you. It's really, really helpful for doing error log checking in HTTP and web environments. So WSK activation poll does the same thing.